Hello, my name is Armand Nicolicioiu and I will be presenting our project on learning diverse features in vision transformers for improved generalization. This is an important topic because deep learning models can be very accurate on standard in-domain data, but they can generalize very poorly on out-of-distribution examples. This can happen because some spurious correlations from the training data can act as shortcuts that are used by the model instead of relying on the robust features. These simple correlations can be, for example, the background color or the brightness settings of the camera that it's used to take the pictures. And the robust feature is the one that we as humans intend to use to classify the data. For example, the shape of some objects. And the goal is to train a model that generalizes to out-of-distribution data and is robust to spurious correlations. To illustrate this scenario of learning with spurious correlations, we use this example. Let's consider that we have a data set with two classes, and the first one is a cow. It can happen that all the cows seen during training are on a green field. This green field is a spurious correlation associated with the presence of the animal that we want to classify. The second class in our dataset is a camel. Similarly, it can happen that all the camels seen are in the desert, so the background color will be somehow yellow. A model again can learn to rely on this simple feature, which is the background color, to make the prediction, and it can completely ignore the presence of the animal. So out of distribution we can have something like this. Different animals, maybe of different types, but in a background that wasn't commonly seen during training. For example, a cow in the desert. This will be wrongly classified by our predictor as a camel because it learned to rely on the spurious correlation. It learned to use it as a shortcut and completely ignore the more complex features. In this project, we started by investigating the vision transformers property for modularity. It is expected that different heads in a multi-head attention layer will learn different predictive features. Then we show that if this happens, we can apply a pruning of the attention heads and remove those that correspond to spurious features. And if we remove them, the out-of-distribution performance will significantly improve. Then we want to further amplify this inherent property that transformers have. And we do this by implementing a diversity regularizer, and this will prevent all the heads from learning the same features. So this leads to higher head specialization, and higher head specialization combined with pruning leads to increased out-of-distribution generalization. First, let's consider the standard learning framework. This is training a machine learning model for empirical risk minimization. Our machine learning model is a hypothesis parameterized by a set of parameters theta, and for a set of examples sampled from a fixed data distribution, we want to minimize the loss obtained by this model. And to evaluate this performance, after training the model on training data, we also have some validation and test splits that we use to measure the accuracy. But the assumption is that all the training, validation, and test examples follow a similar data distribution. During a distribution shift setting, this assumption no longer holds. So the model is trained on in-distribution examples with the same techniques, but at test time, out-of-distribution examples are used. For example, the in-distribution examples in our simple dataset with the cow and the camel are cows correlated with a green field, camels correlated with a yellow background. And the out-of-distribution examples is a cow on the desert. Here there is a change in the distribution. It can happen that training data contains a mixture of robust and spurious predictive features. And if the model learns to rely on the spurious features, it will have bad out-of-distribution performance. But A training dataset can be underspecified, and that means multiple hypotheses are equally likely to model the data. As we saw, if we look at the type of the animal, we can make good predictions, but even if we only look at the type of background, we can make perfect predictions equally well on the in-distribution data, because it doesn't matter if we rely on the spurious correlation, on the spurious features, or on the robust features. If they are perfectly correlated, either one is good enough to model the data. But out of distribution, this correlation might not be present anymore. So if we rely on it, the model will have very bad performance. The dataset that we use in our example is MNIST CFAR. It contains collages of two images. One is taken from MNIST with a digit either 0 or 1, and the second one is taken from CFAR, and it contains either a car or a truck. And during training, we have a correlation between the two images. All the cars are paired with the digit 0, and all the trucks are paired with the digit 1. So, the label is given by either a car or a truck. And a model can learn to rely on this complex feature, but is more likely to rely on the simple shape of the digit and only look at it to make the predictions. And out of distribution at test time, this correlation is no longer present, and a car can be paired with digit 1. And if a model relied on the digit type, it will make a bad prediction, because it only saw the digit 1 paired with a truck, so it will think here it's a truck, but this is no longer true. In our proposed method, we use vision transformers because we want to leverage their property for modularity in different attention heads. And to do this, we designed a head pruning mechanism that can remove the heads associated with spurious predictive features. And to amplify their property for modularity, we introduced a new regularizer that enforces an orthogonality of the features learned by each head. So it will prevent all heads learning the same features. Let's see how this works. For the head pruning mechanism, during the inference of the multi-head self-attention, we compute the output of each head, and before concatenating, we want to prune a subset of the heads, and we do this by setting their value to 0. And then we just scale the final output to compensate for the masked heads. So let's see a scenario. What are the features that each attention head could learn? For example, the first head could look at the object in the image and it can check if it has ears. The second head might look for the presence of a big nose. But the third head might look at the background and check if it's green. This sounds like a spurious correlation that it's unwanted in our model, so we can prune this head. For our diversity regularizer, we compute the input gradient for each attention head. This is defined as a gradient of the top prediction with respect to the shared input. So we can see it in the first equation. This is the input gradient for each head. Then in the second equation, we compute the cosine similarity between all pair of heads. And for our diversity regularizer, we take the squared cosine similarity between all pairs of heads. And we add it to the total loss of the model, weighted by a parameter lambda. Let's look at the results. We observe that empirical risk minimization already leads to a degree of separation between the spurious and robust features learned by the transformer model. And this degree of separation allows our pruning method to improve the out-of-distribution performance. In the first row, we have the performance of this baseline. For in-distribution accuracy, we have 88.8% accuracy, but out-of-distribution accuracy is much lower. That means that the model relied on some spurious correlation that doesn't appear in out-of-distribution examples. But because there is a degree of separation between the features learned by each head, if we only prune the biased heads, we can have an increase in accuracy, which is seen in the third row here. Then the next experiment is training the vision transformer with our diversity regularizer instead of doing empirical risk minimization. And this already has an increase in accuracy compared with the baseline. But it also allows the pruning to achieve even better performance, because the degree of separation between spurious and robust features is even larger. It's amplified by our diversity regularizer, and we can see this in this figure. We want to inspect the behavior during empirical risk minimization and during input gradient diversification. Each line in this plot represents the performance of a different head, and in the first row we look at how well the prediction of each head correlates with the spurious feature, and on the bottom row we look at how well the prediction of each head correlates with the presence of the robust feature. So we see that during empirical risk minimization there is a difference between the performances of each head, but there is still a larger overlap between them. But with our proposed diversification method, the gap between the performances of each head is much larger. So the highest performance achievable by the top performing head is much larger than it was during empirical risk minimization. So applying head diversification followed by pruning gives the best performance out of distribution. In conclusion, we again confirm that transformers can attend to different features, and we demonstrated that if this happens, pruning the heads that corresponds to more biased features can be we can prune the heads that correspond to biased features, and this improves the out of distribution performance. Additionally, we show that the head diversification regularizer that we propose leads to higher head specialization, and this means better out of distribution generalization. Thank you for your attention. Our code is publicly available on GitHub, and we are very happy to answer any questions that you might have.